Good morning. This lesson is for Mat 151, Chapter 11, Lesson 2, the circle and the ellipse. So our objectives for today are given an equation of a circle, complete the square if necessary, and then find the center and the radius and graph the circle. And second objective is given an equation of an ellipse, complete the square if necessary, and then find the center and vertices and the foci and graph the ellipse. So a circle is a set of all points in a plane. They're at a fixed distance from a fixed point called the center in a plane. So we learned the standard equation of a circle in geometry, and then we used it again in algebra 2. So you can see there that the standard equation of a circle, with h and k being your center and r is your radius, you get the quantity x minus h squared plus y minus k squared equals r squared. So if we're given this equation that you can see here, we're going to find the center and the radius and then graph the circle. So first we're going to complete the square, and we're going to have to do it twice, once for the x's and once for the y's. So we're going to take our equation and move our constant to the other side. And notice how we group together the x values and we group together the y values. And then in order to complete the square, remember that equation, b over 2 squared is how we complete the square. So when you do that, if you look at our negative 16, which is our first b right here, negative 16 divided by 2 will give you negative 8. And remember, we're going to remember that negative 8 because it's going to come back to us. But when we square that, we get 64. For this piece, we have 14. 14 divided by 2 is 7. 7 squared gives us 49. So we're going to write those in those blanks, and then we also have to add each of those numbers to the other side. And then this part and this part give us perfect square trinomials. And so when we factor those, remember that's where we get the x minus 8 and the y plus 7 there. And then this side simplifies to the 81. Okay, they're going to rewrite that so that they have a minus sign there. Okay, and then that shows us that this piece 8 and the negative 7 is our center, and then 81, the square root of that is 9, so 9 is our radius. So we're going to take those two pieces of information and plot it on the graph. So there's 8, negative 7. And then you use your radius. You can either count up and make a point, count over, make a point, count down, make a point, count to the left and make a point, and then we can just connect those points with a smooth circle. Okay, an ellipse. An ellipse is a set of all points in a plane, the sum of whose distances from two fixed points, the foci, is constant. The center of an ellipse is the midpoint of the segment between the foci. The major axis of an ellipse is longer than the minor axis. So in this example, you're going to see that this is longer, so this has a vertical axis. Sorry, not vertical, horizontal. So horizontal is the first one. So that uses this equation here. X squared plus y squared over a squared plus b squared equals 1. Where when your major axis is horizontal, we get vertices at negative a0 and a0, and our y-intercepts are at 0, negative b, and 0, b. And then our foci, we find the foci by using this equation here. It looks very much like the Pythagorean theorem, except for it's not a plus sign between your a and b, it's a minus sign. Okay, so in this case, we're going to do a squared minus b squared equals c squared. And then when we do that, we find our c. So let's look at an example. Here we have the major axis is vertical. So in this case, we have everything's the same except for b squared comes right here and a squared comes there. And again, a is greater than b is greater than 0. So that's how you can tell whether you have a major axis that's vertical or a major axis that's horizontal, is which one has the bigger value. Whichever one has the bigger value, okay, determines whether it's vertical or horizontal. So when this one is the bigger value, then it's horizontal, and when this one is the bigger value, then it's a vertical. So our vertices for this one are going to be at 0, -a, 0a. So you see those on the graph. And then the x-intercepts are going to be at -b0 and b0. And then of course our foci, 0, -c, and 0c. And again, we can find that foci using this equation. So in this example, it says find the standard equation of the ellipse with vertices at -5, 0, and 5, 0, and foci -3, 0, and 3, 0. And then it wants you to graph the ellipse. So because our 5 is greater here with these, and we have a foci of this is going to tell us that we have the major axis is horizontal. And it's centered around 0, 0. So that is our center for our ellipse. So we have this format for our equation. Okay, and already because we have this, we know that our A is 5. So in order to find our B, we're going to have to use that equation where we plug into the a squared minus b squared equals c squared, where a is going to be 5 and c is going to be 3. So we're going to plug those in and then square them. And then if I take the b squared to the other side, it will become positive, and 9 will become negative, and that's going to simplify to 16. So that if we take the square root of 16, we get 4. So that's going to be our equation when we plug in a squared and b squared. We simplify that. Here's the equation of our ellipse. Now we can use our vertices. We know that because b was 4, our y-intercepts are going to be 0, -4, and 0, 4. And so we're going to plot those vertices, our x-intercepts, and then connect those with a smooth curve. So here's -5, 0, 5, 0, 0, 4, and 0, -4. And then we're just going to connect those. For this example, they gave us 9x squared plus 4y squared equals 36. So we're going to find the vertices and the foci and then draw the graph. So first we're going to find the standard form. Notice it's almost there. Okay, we just need to get this number to be a 1. So we're going to divide everything by 36. When that simplifies, we end up with this equation, because 9/36 simplifies to 1/4, 4/36 simplify to 1/9. Of course, that was getting 1. Now we're going to see what these are squared to find our a and b. So 4 becomes 2 squared, 9 becomes 3 squared, and because this one is bigger, then that tells us that we're going to have this with a vertical. So a is 3, b is 2. And so we know the vertices are 0, -3, and 0, 3. And then we're going to use this to find our foci. So we're going to plug in our 3 and 2 for a and b. So 3 squared gives us 9, 2 squared gives us 4. If we subtract those, we get 5. But then remember that c squared equals 5. So square root of 5 is just rad 5. So our foci is at 0, -square root of 5, and 0, square root of 5. And because b equals 2, then our x-intercepts are at -2, 0, and 2, 0. So then we're going to plot those points. So you can see the negative, or the 0, 3, the 0, negative 3, 2, 0, negative 2, 0, and then there's our foci at 0, square root of 5, 0, negative square root of 5. Of course, we're only going to connect these points on the outside. So the standard equation of an ellipse with center at HK and your major axis is horizontal. You can see here, like several of the other equations that we've had where we had a center other than the origin, okay, we always subtract h and k from our y or our x inside our parentheses, and then of course because we're squaring it, that stays the same. So when you go to find your vertices, then we have to do a little bit more math here. Okay, the k is going to end up to be whatever that point is for a major axis when it's horizontal, but for the x value, it's going to be h minus whatever our a is, and then for this one, h plus a. Notice the k stays the same. So the length of our minus axis is going to equal 2b. So whatever b is, we would double it. Okay, for the foci, okay, we're going to have h minus c for the x value. K stays the same. H plus c for the x value. K is our y value. When we can still use this equation to find b if we're not given it. So if we do that, here's what it looks like so far. Okay, so let's look at this example here. We're going to go through and see if we can put it into our standard form and then identify the center, the vertices, and the foci, and then draw the graph. So again, first we're going to have to complete the square twice. So we'll move our 21 over. So that's going to become negative. Okay, then when I grouped the 4x squared and the 24x, it has a common factor of 4, so we factored that out first. So again, we're going to go through and we're going to use that equation, b over 2, and then square it. So in this case, our b is 6. So when we plug that in, 6 divided by 2 gives us 3. So keep that in mind, the 3. If we square the 3, we get 9. So we're going to complete this square with a 9. On this one, we'd have a negative 2 divided by 2 gives you a negative 1. But when you square it, it becomes a positive 1. But notice, because this one has a 9 here and a 4 on the outside, we're really multiplying that number by 4. So notice on this side, we're doing a 4 times 9. Okay, this one didn't have anything on the outside, so we're just adding the 1. But when we simplify that and we take the factored form of this perfect square trinomial, we get the x plus 3 raised to the second power, and this one, y minus 1 raised to the second power. Okay, and so the last thing we need to do is we need to get this part equal to 1. So remember, like we did before, we're just going to divide everything by 16. So when we do that, then we end up with this equation here. Because 1/16 times 4 is going to give you just a 4 in the denominator. This one gives you the 16, and of course that simplifies to a 1. And then to find your a and b, we're going to see what these numbers are squared. So that gives you 2 squared and 4 squared, and then they're just rewriting it with the minus sign. So negative 3 is your x value of the center, and 1 is your y value. And then your a is 4, your b is 2. So there's your center, negative 3, 1. A is 4, B is 2. The major axis then is going to be 4 units above and below the center, so that's why we have to add those or subtract them. So when we put that together, we get -3, 5, and -3, -3. And then to find our C, we're going to plug in 4 for A and 2 for B. And so 4 squared minus 2 squared, that's 16 minus 4 gives you 12. So then we're going to take the square root of that, which is 2 rad 3. And remember, it could be positive or negative, so that's why over here we do 1 plus that number, 1 minus that number. And that can't simplify, so we can just leave it as the radical. So those are where my foci are at. And since B equaled 2, the endpoints of our minus axis are 2 units to the right and left of center. Okay, so we add the 2, we minus the 2 from that, so that ends up at -1, 1 and -5, 1. Now we're going to take all of those things and we're going to plot them on our graph. So you can see for our major axis, we end up with the -3, 5 and the -3, -3. For our minor, we get -5, 1 and -1, 1. And then there's our foci here and there, and our center is at -3, 1. Then we just connect with a smooth curve around that ellipse. Okay, some applications that we might use ellipses for in real life. This one says an exciting medical application of an ellipse is a device called the lithotripter. One type of this device uses electromagnetic technology to generate a shock wave to pulverize kidney stones. The wave originates at one focus of an ellipse and is reflected to the kidney stone, which is positioned at the other focus. Recovery time following the use of this technique is much shorter than with conventional surgery, and the mortality rate is far lower. So that means people survive this without dying, and so it's very effective. They don't have to cut into anybody. They can just use these shock waves in order to break up those kidney stones. Another use of the foci is a room with an ellipsoidal ceiling is known as a whispering gallery. In such a room, a word whispered at one focus can be heard at the other, clearly, like as if they're standing right next to you. So whispering galleries are found in the rotunda of the Capitol building in Washington, D.C., and also in the Mormon Tabernacle in Salt Lake City. Ellipses have many other applications, like planets travel around the sun in elliptical orbits with the sun at one focus, for example, and satellites travel around the Earth in elliptical orbits as well. Okay, so everything kind of goes in an elliptical pattern, not necessarily circular pattern. Okay, so that's the end of this lesson. So you guys can go ahead and work on your Math Excel assignment 11.2.